In this video, we will solve examples of problems finding eigenvalues and eigenvectors for 3x3 matrices. So this first matrix here, minus 4, minus 2, 4, 4, 2, minus 16, 1, 1, minus 7, we want to find the eigenvalues and corresponding eigenvectors. So we'll want to do determinant of a minus lambda I here to figure out what these eigenvalues are. So the matrix a minus lambda I is minus 4 minus lambda, minus 2, 4, 4, 2 minus lambda, minus 16, 1, 1, minus 7, minus lambda. In order to find these eigenvalues, I want to find this determinant here. And probably the easiest way to do it is to use row reduction. Once we swap the rows around to put something that doesn't involve lambda in the top left corner. Now, as we do this, we're looking for places where the determinant is 0. That fact is not changed by minus signs or multiplying by constants, because 0 times a constant is still 0. So I can do any of my row regressions that I want, and it's not going to affect the determinant in a way that changes the eigenvalue. So for this, I'm going to find determinant of a minus lambda I, which will be the same as, up to a minus sign, the determinant of 1, 1, minus 7, minus lambda, 4, 2 minus lambda, minus 16, minus 4 minus lambda, minus 2, 4. And I'm going to use this 1 to cancel out the 4 and the minus 4 minus lambda that are here. So R2 is R2 minus 4 R1. R3 is R3 plus 4 plus lambda, R1. So from this, we will get 1, 1, negative 7 minus lambda. We'll get 0, 2 minus lambda minus 4, and minus 16 plus 28 plus 4 lambda. We'll get 0. We get minus 2 plus 4 plus lambda, and then we will get 4 plus 4 plus lambda minus 7 minus lambda. And now I want to simplify this 2 by 2 bit in the bottom corner. 1, 1, minus 7, minus lambda, 0. This is a minus 2 minus lambda. This will be a 12 plus 4 lambda, 2 plus lambda. And this here becomes a minus 28 minus 7 lambda, minus 4 lambda, minus lambda squared. I'm going to end up here with a negative lambda squared minus 11 lambda minus 24, because 4 of that will cancel with the 28. And now we can work out this determinant, which will equal the 1 from up here, and then times this determinant down here. So I will get a minus 2 minus lambda times negative lambda squared minus 11 lambda minus 24, and then minus 2 plus lambda, 4 lambda plus 12. Now, I see that off the bat, I can immediately factor out a lambda plus 2 from both terms here, which is going to make my life a lot easier in trying to find these eigenvalues. So I'll get a lambda plus 2, and then times a negative sign going in here, lambda squared plus 11 lambda plus 24, and then a minus sign going into 4 lambda and 12. Plus the lambda plus 2, lambda squared, plus 7 lambda, plus 12, and that factors as lambda plus 3, lambda plus 4. So my eigenvalues are lambda 1 is minus 2, lambda 2 is minus 3, and lambda 3 is minus 4. So with that, we can now find the corresponding eigenvectors. So the first eigenvalue, lambda 1 is minus 2. We go back to the matrix at the beginning, and we're going to add 2 along the diagonal. And if we do that, we get the following matrix: minus 2, 4, 4, 4, minus 16, 1, 1, minus 5. Now I could do some row swapping here, or based on what I see, I'm going to divide the first row by minus 2 and the second row by 4. Again, we're just doing row reduction. We're not tracking for determinants, so it doesn't really matter what we do as long as we do row reduction correctly. So I'm going to do row 1 over minus 2 and row 2 over 4. to give me 1, 1, minus 2, 1, 1, minus 4, 1, 1, minus 5. And you can kind of see what's going to happen after one more step. The first two columns are all going to go away at the same time. So if I do row 2 is row 2 minus row 1, and same with row 3, I end up with 1, 1, minus 2, 0, 0, minus 2, 0, 0, minus 3, which when I row reduce again will become 1, 1, minus 2, 0, 0, 1, 0, 0, 0, which tells me that v3 must equal 0, because that's this equation here. And the first equation, when I drop the v3 term, will tell me that v1 plus v2, it would be minus 2 v3, but that's gone, equals 0, so v1 is negative v2. So for the vector here, I can get 1, minus 1, 0 is a set of values that solve these two equations. Therefore, they are an eigenvector for eigenvalue minus 2. We can now move on to the next eigenvalue, lambda 2, which is minus 3, and also get our matrix by adding 3 on the diagonal instead of adding 2, which gives the following matrix. This time I'm going to do a row swap. I'm going to swap rows 1 and 3 to set up the row reduction that way. And then I'm going to add 1 copy of row 1 to row 3 and subtract 4 copies of it from row 2 to get rid of those two entries to give me 1, 1, minus 4, 0, 5 minus 4 is 1, negative 16 plus 16 is 0, and I get 0, minus 1, and 0. This looks a little odd, but it's actually going to be okay. My next step is going to be to cancel out that minus 1 at the bottom by doing row 3 is row 3 plus row 2. Give me the following, 1, 1, minus 4, 0, 1, 0, 0, 0, 0, which is in row echelon form. In equation form, this tells me that v1 plus v2 minus 4v3 equals 0, and v2 equals 0. So v2 is 0, this term is gone, and I'm left with v1 equals 4v3. So if I pick v3 to be 1, v1 is then 4, and so my eigenvector, vector v2, is going to be 4, 0, 1 for this eigenvalue. And then finally, the last eigenvalue, lambda 3 is minus 4. We're now adding 4 on the diagonal instead of 2 or 3 to give the matrix. Looks like this. Now in this case, because I see a 0 up top here, I need to swap rows. So let's swap row 3 up there again. And then use this 1 to cancel out this 4. So R2 is R2 minus 4R1, which gives us 1, 1, minus 3, 0, 6 minus 4 is 2, negative 16 plus 12 is minus 4, 0, minus 2, 4. And hey, we're in good shape here. Those bottom two rows are going to cancel. So the row reduction process will lead us to 1, 1, minus 3, 0, 1, minus 2, 0, 0, 0, which means that in terms of components, we have v1 plus v2 minus 3v3 is 0, and v2 minus 2v3 equals 0. Then we know that v2 is 2v3, and then plugging that in up top, we get v1 plus 2v3 minus 3v3 is 0, or v1 equals v3, which means as a vector here, I can take 1, 1, and 2, with the 2 in the middle to correspond to the v2 term, as my eigenvector. So now let's collect our answers. So for the matrix A, the eigenvalues and eigenvectors are, we have lambda 1 being minus 2, lambda 2 was minus 3, and lambda 3 was minus 4. And they corresponded to eigenvectors. v1 was 1, minus 1, 0. v2 was 4, 0, and 1. And v3 was 1, 2, and 1. That is a final completed answer for finding the eigenvalues and eigenvectors of a 3x3 matrix. In this case, we had 3 real and distinct eigenvalues, so we knew we were going to get 3 linearly independent eigenvectors for this matrix that can form a basis for R3, or whatever else we want to do with this type of problem.